Jackson. We're going to continue looking at the mean value theorem just a little bit, and we're going to look in this video at a couple of applications or uses of the mean value theorem and maybe get a little bit better idea of what it actually tells us. So let's start with a few exercises here. The first one is verify that the following function satisfies the hypothesis of the mean value theorem. Find all values of c satisfying the theorem and illustrate this result graphically. And the function we want to look at is f of x equals ln of x on the closed interval from 1 to 4. See if you can work this out yourself and come back and check your answers with me in just a minute. Press pause now. Okay, maybe we should just refresh our memory on the mean value theorem really quickly. What it says here is let f be a function such that f is continuous on a closed interval from a to b and differentiable on an open interval from a to b. Then there exists at least one value c in that interval from a to b, such that f prime of c equals f of b minus f of a over b minus a. Graphically, what this says is if we have a function that there's like this blue function here, and if we look at the secant line across here and look at its slope, the secant line segment, then the slope that we get is exactly the right side of this equation right here. And the left side is the slope of the tangent line at some point in between. And what the mean value theorem says that there's some point in between here, say right here, where the slope of this tangent line is the same as the slope of this secant line. Okay, so with that in mind, if you haven't already worked this problem, try it now. Press pause. Okay, so we know that the natural logarithm function is differentiable on its entire domain from 0 to infinity, not including 0. So this function satisfies the hypothesis of the mean value theorem. So the conclusion of the mean value theorem says there's at least one value c in the interval from 1 to 4, open interval, with f prime of c equals f of 4 minus f of 1 over 4 minus 1. Okay, let's see, the f of 4 is natural log of 4, f of 1 is natural log of 1. Natural log of 1 is 0, so this becomes ln of 4 over 3, which is the derivative. Okay, now the derivative, on the other hand, of natural log of x is 1 over x, so the derivative at c is 1 over c. So we just want to find a value where these two things are equal, and of course it needs to be a value between 1 and 4. So we just set the derivative equal there, and just solve for c. So reciprocal both sides, we get c equals 3 over natural log of 4. And if we plug that in our calculator, we see that in fact it is a number between 1 and 4, about 2.16 something. So that is the value of c that we're guaranteed by the mean value theorem. In this case, there's only one such value between 1 and 4, but in general, there might be more than one value in some cases. In this case, there's only one. Now let's illustrate that graphically. So y equals ln of x from 1 to 4 is this blue graph. Okay, the secant line segment in green then is y equals the slope, which is ln of 4 over 3, slope of the secant line, times x minus 1, plus 0. Okay, because it goes through the point 1, 0. So there's the point slope of that formula, or the x-intercept slope x-intercept form of that line. And of course that's going to be defined from 1 to 4 to get that secant line segment. The c value that we're looking for is 3 over ln of 4, and of course the y value that goes with that is ln of 3 over ln of 4. Okay, and so that's the point, the red point right here of tangency. And then we make a tangent line with the same slope as the secant line, which is ln of 4 over 3 times x minus this x value of 3 over ln of 4 plus the y value, ln of 3 over ln of 4. Of course, this x minus the x sub 0 is in parentheses. The y sub 0 is over here. The slope m is here. That's the point slope form of a line through that point with the proper slope. And we see that the purple line is the tangent line there, and it is parallel to the green secant line. Okay, why is the this theorem called the mean value theorem. What does the word mean imply here? Well, the word mean refers to the statistical mean, or in other words, the average. Okay, so the mean value theorem says that the instantaneous rate of change at some point on the interval must be the same as the mean rate of change over the interval, the average rate of change. Remember, the average rate of change, or the mean rate of change, is the slope of the secant line. The instantaneous rate of change is the derivative. Now, suppose that one makes a trip of 30 miles in 25 minutes. What does the mean value theorem tell us about the speed we travel? See if you can answer this question. Press pause now. Well, what's the average rate of change for the trip? Well, it's 30 miles in 25 minutes times, so it's 30 miles over 25 minutes is the rate of speed. We're going to convert to miles per hour, and so that's 60 minutes over 1 hour, so that minutes cancel and you get miles per hour. In fact, you get 72 miles per hour. 30 divided by 25 times 60 is 72. So that is 72 miles per hour. That's the average speed for the entire trip. And what the mean value theorem says, there's at least one point in that trip when you are going exactly 72 miles per hour. Could have gone above it some and below it some. It averages out to 72, but there has to be at least one place where it was the car, let's say, was going exactly 72 miles per hour. So if we can kind of turn this around backwards and say that another interpretation of the mean value theorem is that the function cannot increase or decrease over an interval at an average rate more than the maximum absolute value of the derivative on that interval. So if we know something about the derivative, then that tells us something about the average rate of change. So notice the previous problem, we knew the average rate of change, and we were trying to find the derivative, the instantaneous rate of change. And this one we're going to kind of turn it around. What if we know something about how big the derivative is? That actually tells us something about the average rate of change. Okay, so let's see if we can work that in a problem here. Suppose that f of 3 equals 5, and f prime of x is less than or equal to 4 for every value of x everywhere. Okay, what can we say about f of 6? See if you can figure this one out. Press pause now. Okay, hopefully you've thought about this a little bit. And so notice that the derivative is defined everywhere, so the hypothesis of the mean value theorem is satisfied, certainly on this interval from 3 to 6. So according to the mean value theorem, there exists some value of c in the interval from 3 to 6, so that f of 6 minus f of 3 over 6 minus 3 is f prime of c. Now 6 minus 3, of course, is 3. F prime of c, however, is less than or equal to 4 for all values of c. Right? All values of x. So all values of c, this would be true. Well, that means this f of 6 minus f of 3 over 3 is less than or equal to 4. So f of 6 minus f of 3 is less than or equal to 12. Multiply both sides by 3 there. But now let's see. That means f of 6 is no bigger than, or is less than or equal to, f of 3 plus 12. We can only increase at most 12. So the rate of change can only be up to 4, and we're going over 3 units, so that most we can go up is 12. But f of 3 started at 5, so the highest we can be is 17. So f of 6 is less than or equal to 17. Okay, if it was bigger than 17, then there would not be a place in between where the slope of the tangent line would equal the slope of the secant line, and so it would violate the mean value theorem. That's not possible. So f of 6 has to be less than or equal to 17. Okay, here's a similar problem. See if you can do this one now. If a speedometer always registers between 65 miles per hour and 75 miles per hour for a 2-hour trip, how far could the car have traveled? See if you can figure that out. Press pause now. All right, well, what does this have to do with the mean value theorem? Well, Since distance is a differentiable function, the hypothesis of the mean value theorem is satisfied, or distance, or maybe I should call it position, is a differentiable function. And of course its derivative is the velocity. Since the distance traveled is the change in the position, where p is the position, so d is delta p, the slope of the secant line then is delta p over delta t, which is d over 2. So d miles over 2 hours. That's the slope of the secant line. That's the average rate of change. But according to the mean value theorem, at some point on the trip, that slope of the secant line, d over 2, has to be the same as p prime at t for some point in the trip. Let's say t equals c, and we'll say this is at that value c. And of course, p prime of c is the velocity. Okay, so the velocity has to be the same as the slope of the secant line. But we're told, okay, that 65 is less than or equal to the velocity, which is less than or equal to 75. So the velocity, or at least the absolute value of the velocity, the speed, is between 65 and 75. So the distance traveled divided by 2 has to be between 65 and 75. So the distance, multiply everything by 2, and the distance traveled has to be between 130 and 150. In other words, if you go, the lowest you could be is 65 miles per hour for 2 hours, which is 130 miles. And the farthest you could go is if you went 75 miles per hour for 2 hours for 150 miles. So it has to be somewhere between that. And this is a consequence of the mean value theorem. Now we can also use the mean value theorem to prove a couple of other important theorems. There's a couple of important theorems we've been using about derivatives already, but let's go ahead and prove those formally with the mean value theorem. So for example, here's an exercise for you. Use the mean value theorem to prove that if the derivative of a function is 0 everywhere on an interval, then that function is constant on that interval. See if you can work that out. Press pause now. So we're given that f prime of x equals 0 for all x in an interval a to b. Since the derivative exists on the interval, the hypothesis of the mean value theorem is satisfied. Let u and b be any elements of that interval from a to b, and let's let u be less than v. So we just pick two numbers in there, order them left or right, u to v. Let the mean value theorem be applied to f on the interval u to v, and there exists at least one value of c in this interval, well, actually in the interval u to v, which is also in the interval a to b, with f of v minus f of u over u minus v equals f prime of c. However, the derivative is 0 for all x in the interval a to b, so certainly its derivative is true for any in between u and v, including c, so that derivative is 0. So we can substitute 0 there. Now multiply both sides by u minus v, and we get f of v minus f of u is 0, which means f of v equals f of u, which means that the value of f is the same. Since u and v were arbitrary elements, this means that f is a constant function on that entire interval from a to b. Okay. How about this one? Prove that two functions have the same derivative on the interval if and only if they differ by constant, and thus their graphs are vertical shifts of each other. See if you can prove that one on your own. Press pause now. Well, the first direction says, suppose that the functions differ by a constant, f of x equals g of x plus c, for some constant c. Well, all we have to do here is apply first the sum rule for derivatives, and then the constant rule for derivatives. And what we see is then that f of prime equals g prime. So sum rule says it's the derivative of the first plus the derivative of the second. The derivative of the second is 0. And of course we get that. So So we've done that many times. Let's reverse it now. Suppose that for all x in an interval from a to b, f prime of x equals g prime of x. Let h of x be f of x minus g of x. Now by the sum and constant multiple rules, we have that the derivative of h is the derivative of f minus the derivative of g. But we know that the two derivatives, let's see, we know that that's going to be 0 for all x in the interval, because they have the same derivative, right? That was our hypothesis, right? Our hypothesis right here was that they had the same derivative. So that difference right there is 0. So h prime is 0 for all x in that interval. Now, our previous exercise said that if the derivative function is 0 everywhere on the interval, then that function must be constant on the interval. So h is a constant function. So h of x equals just a c for some constant c, but that means f of h is just f of x minus g of x, so f of x equals g of x plus some constant c. And of course that means that they differ by a constant, and of course that also means that f is just a vertical shift of g, and vice versa. In our next video, we will use the mean value theorem to prove an extension of it called Cauchy's mean value theorem, which we'll in turn use to prove L'Hopital's rule, which is useful for finding some limits.